We good?
Exposure, select set, cap brackets to can. It's going.
We're on, okay. We're going to do something today, interestingly enough, my Calc 3 lecture this morning, the first half of our class is going to be exactly what they did the first half of their class, because then I segued that into the three-dimensional version of what we're doing, because everything in Calc 3 is a three-dimensional version of everything in Calc 1. But the application we're doing is it's a pretty big one, but it's not a hard one. But it's a really cool one because we only need the calculus we have now to be able to pull it off. Okay, so I'll kind of leave it at that. So we have two major themes today. One is an application and one is a new type of problem that we're going to look at the second half of class. So here's the question, okay? I want to estimate the square root of 16.1. I have no technology, though. I'm out in the field. Or, quite simply, I am math for several hundred years when no technology existed. But I want to estimate the square root of 16.1. So if I asked you, you'd say, well, it's a little more than 4, and you'd be correct. But I would actually like to do better than that by using what I do know about calculus and functions and things. So what we're going to look at is what is called asymptotic convergence. It sounds kind of scary, but it's the idea that I'm going to choose something that acts the same way, and its numerical values might be a little bit easier to work with. So let's consider, first of all, the graph of the square root function. Okay? So if I look at this graph here, now, let's say that point right there, that's 16, and so when I go over here, that's square root of 16. That one I know. That one's easy. But what I want to do is move just a tiny bit away from 16. You know, here, let's say that's 16.1. So that's really close, but it is definitely not the same value. So what can I do? Well, one thing I can do is what if I drew the tangent line at the point 16 comma square root of 16? Because that's a nice happy number, right? That's 16 comma 4. That number's easy to work with. If I drew the tangent line, then the point on the curve that I'm looking for, is it going to be pretty close to the point on the tangent line? Think about that. The tangent line is leaving the curve, but not very much. So on the tangent line, if I use that y value as my best estimate, then I might be relatively close. And this is the entire thought process we're going to do today. This is the whole thing. So I'm going to take this little piece, I'm going to blow it up. Okay? So here's what we've got. Okay? So right here, this is 16 comma square root of 16. That's that point. Now, there's my tangent line. There's my curve. This is the point I want. This is 16.1 square root of 16.1, whatever that is. But I want to use the y value on the tangent line. I want to use this y value to estimate this y value. Now in my picture, there's a really big separation. Is the separation really very much, do you think? No, it's actually going to be tiny. And so the value on the tangent line is probably going to be really close. Now, computing the value on the tangent line is actually going to be simple because I'm using nice numbers. So let me get into some of the notation. On the curve, this is the actual change in x. This is the actual change in y. There's no question about that. So if I went over to here, let's say that's the square root of 16.1. The difference in these is the change in y. Okay? This separation is exactly what delta y is. This separation here is exactly what delta x is. So another way to think about this, if I asked you, then the square root of 16 plus delta x, that should be the square root of 16 plus delta y, shouldn't it? So again, that value plus that value. I just don't know what the square root of 16.1 is. But I do know whatever that change is, this would give me exactly the answer. I want to estimate this, and I want to use the tangent line to do it, okay? So, going back to the picture, the actual change in the x for the curve, the actual change in y for the curve. Now, if I look at the tangent line, the symbol we use for the change on the tangent line is what we call a differential. We actually use a dx for this. Dx refers to the change on the tangent line, which means that that value right there we call dy. I'm going to use dy as my best guess for what the actual change is. Because I know whatever I get, I'm just going to add it to the square root of 16 at some point. Okay? So, how do I do that? So this is the symbol we're using. We're going to say that delta y I'm going to estimate with dy. Now this is a really important symbol, and almost all people that I run across use it incorrectly. They don't understand what the symbol means. This has absolutely nothing to do with any form of a numerical calculation. If you're using this after a number, you're using the wrong symbol. This means asymptotic. It means they're connected asymptotically. How many remember drawing hyperbolas in algebra? Remember the little dotted lines? And the hyperbola kind of disappeared into the dotted lines? What are those dotted lines called? Asymptotes. Does the curve actually intersect the lines?
No.
Or does it kind of, it gets closer and closer and closer? If I draw y equal 1 over x, doesn't that kind of disappear into the x-axis? The x-axis is an asymptote. This is what asymptotic behavior is that I have a function and my graph kind of almost becomes that function, but an asymptote is a line. Asymptotic behavior, it doesn't have to actually be a line. So there are three symbols, and we often misuse them when they're used in connection. We have this one, we have this one, we have this one. They mean three very different things. In fact, there's no overlap. One is not the other. This is equals. This means that I have an exact value. So I'm done at the end of the problem, and I said x equals the square root of 2. That's my answer. Okay? Now, you're in the chemistry lab, and you need square root of 2 milliliters of fluid. Is that a problem? Does the beaker have a square root of 2 notch on it? No. So you're going to need to do a decimal approximation. I had a calculator here. Somebody give me a decimal value for the square root of 2. Oh, here it is. Here it is. So if I wanted to do the square root of 2, now it doesn't matter how many decimals, but I know that if I give a few places 1.414, maybe I'm going to go back. Do I say square root of 2 equals this value? Because if I say that square root of 2 equals 1.414, and now I square both sides, I have a problem. Because the left side is a 2. The right's 1.999396. And I'm pretty sure these values are not equal. Equal means equal, exactly the same. This is an infinite non-repeating decimal. I need to round it off because it's silly to try to report a bazillion decimal places. When somebody asks you for your GPA, how many decimals do you give them? You give them 100 decimal places, or give them one? Probably. Probably one. Is it rounded off? Probably. But nobody has a problem with that. So rounding is fine, but that's the definition of an approximation. That's an exact value, that means approximation. And you generally only use approximations on irrational numbers. Because if your answer is a fraction, you just write the fraction. How many have had statistics? Are there occasions when you have astronomical numerators and denominators because you're using combinations and permutations and things like that? Right? You have astronomical values. Well, your final answer is a fraction, but you have a 12-digit number over a 13-digit number, and that's my answer. I have no idea of the size of that value. So it's appropriate to give a decimal response, even though it's a rational number, because it's not a usable number as is. That's really the only exception. Otherwise, you never approximate rational numbers. You don't approximate a half. It's just a half. But you approximate irrational numbers. Right? If I needed a value for pi, I'd give as many decimals as I need. But it's irrational, so I'm rounding it off. This means asymptotic. In a numerical sense, this is like saying estimation. Now, there's a historical estimator for pi that was used for over 2,000 years. It's actually, I want to say, on the order of like 2,300 years. Does anybody know what the estimator is for? And by the way, a lot of textbooks still have this. Pre-calculators, what do you think? Remember?
22/7.
Beautiful. Pi is very, very well represented by 22/7. By the way, before calculators. People say, well, wouldn't we have estimated it with 3.14? Nobody in human history has ever estimated pi with a decimal. Because the moment you had one of these, you had the ability to give as many decimals as you want. Why would you use 2 decimal places when you could do as many as you want? No, if somebody told you that a historical estimator of pi was a decimal value, they're pulling your leg. Nobody ever used a decimal before calculators were invented, and pi keys on calculators came pretty quickly. No, it's a really good estimator of pi if I don't have a calculator, but if I have a calculator, I just use the calculator.
Does that mean if you went back in time before calculators and used decimals, no one would know what you're talking about?
Well, but nobody knew anything. They didn't know any decimals. You'd have to actually do things by hand or computers. The first computers that actually could calculate pi weren't even invented until the 1960s. Our ability to do things. The ancient Greeks knew of pi. They didn't have a numerical value that was very accurate, but over time, I was telling my class this morning, I was giving an exam a few years ago, and I forgot to bring work, and I forgot to bring my Sudoku book. So I sat there for 2.5 hours, and I had a choice. I could thumb wrestle, or I could just play around with my calculator. So I played around with my calculator for a few minutes, and I came up with this, which, by the way, is the best I've ever seen in my life. I've never seen anything like this. I literally messed around for a while. Do that on your calculator. What do you notice?
It's very close to,
I think it's at least the first 6 decimals of pi.
yeah.
Does that equal pi? No, but it's a really good estimator of pi. But if I was going to do this, I'd probably want to use a calculator, in which case I'd just use my pi key. So it's kind of a useless endeavor. Asymptotic. Now I'm going to show you an example of asymptotic behavior, because this is one of the most important parts of calculus, and a lot of people don't realize it. We think of everything as being an equal, but not everything is equal. If you've had statistics, nothing is ever equal. You use samples to make predictions about populations, but nothing you do can be equal because you didn't have all the values, and sometimes all the values are too many values. Okay, so let me go, I'm going to show you something. Oops. This is my favorite example to use, I'm about to do. Oops. I'll hold this one off for a moment. All right, I just drew this graph right here. Okay, I'm gonna explain what this symbol means, because this is the most important symbol you're learning today. I just drew the graph. Now, we're not doing graphing yet. That's coming soon enough. But tell me about the domain of this function. Tell me about the domain. Is it everything?
Doesn't include 1 or -1.
Good, except for plus or minus 1. And when my denominator can't be plus or minus 1, but my numerator can, that's not a removable discontinuity, it means I have asymptotic behavior, the vertical asymptote, the evil ones. So I have a vertical asymptote here. You don't see the dotted lines, but there's dotted lines here. Okay, why am I showing you this? Because what I want you to do is back up and keep going back further and further away from this. So I want you to look at this from further and further and further away. So what I'm going to do is I'm going to change the input and output just to make it easier. So I'm going to have x go from -100 to +100. And then I'm going to have y go from, let's say, -10 to 10,000. Okay? Huh. Now, I still want you to back up. I want you to keep backing up. I want you to keep backing up. That evil function just a moment ago with all the different graphs that you just saw and all that, remember they had asymptotes? I haven't changed anything. I'm just having you back up further and further away. Gosh, what does that look like?
Parabola.
That looks like y = x squared, doesn't it? That is so weird. Okay, wait, just for fun, let me draw y = x squared. I'll have 2 graphs at once now. Okay, now let me. The red is my original evil graph with all the weird stuff happening. Blue is the y = x squared. As I get further and further away, do you see any red here? No. To the naked eye, these graphs look exactly the same, don't they? Is that weird or what? No, you actually addressed this issue earlier when we did infinite limits. If I do the long division, this is equal to x squared plus 1 over x squared minus 1. What is this called again? Starts with a T. That's it?
Transient?
It's called a transient term. When we did limits, right, when we did quotients of polynomials and we multiplied top and bottom by 1 over x to a power, and we got numbers, and then we got a lot of these kind of things. As x gets bigger and bigger, this thing is literally going away. Its contribution is less and less and less and less. So if I draw the graph of y equal this and y equal x squared, they become indistinguishable really, really quickly, don't they? Because the difference between them is this quantity here, which is getting smaller and smaller. How can I prove it's indistinguishable? Because none of you can see two different graphs right now. You see only one graph. There are two different graphs, but the difference between them is microscopic. So here's the correct and the very formal mathematical notation. This is, if you don't get anything else today, hopefully you'll get this. This function here is asymptotic to this function here. Because when I drew them together, you can see they're almost exactly the same. And here's one of the cool things about something like this. You're out on the field, you don't have a calculator. I need you to calculate this value, and I need you to calculate it for roughly x equal 1,000. Well, I'll just do x equal 1,000 here. My answer is going to be almost exactly the same. It's much easier using this one than this one, would you agree? And the bigger x is, the more accurate it becomes. Like I said, all of statistics is based on this concept. This is what is called asymptotic convergence, is the things kind of disappear into each other, but they're not equal, and I'm not doing calculations. So that's what the squiggle is. Next semester in Calc 2, this becomes a very dominant theme for the types of problems you're going to be performing. So let me get rid of this. I don't need that anymore. Okay. Now, going back to the problem that we have. When you are doing something numerical, now, is it very clear that the line is leaving the curve? Is that clear? So no value on the line could ever equal any value on the curve, and it's not an approximation. Approximation means I'm giving you a number, you're calculating it on your calculator, but you got to round it off because there's, reporting infinitely many decimals takes way too long. Right? It might take you all day to report infinity, right? So you round it off. That's an approximation. But when I'm escaping the line, they're not equal. I'm using one as an estimate of the other. Are we losing something? Make sure we're still on video.
I think.
Does it say standard?
Yeah.
I remember one of the choices is time lapse and one of the choices is photo. Those are bad choices. Time lapse means the whole lecture is in about 3 minutes. Photo means we got about 10,000 separate pictures. So I want to do an estimation. I'm not doing an equals. I'm taking the value on the tangent line and I'm going to use that to estimate the value on the curve because it's way, way simpler. Okay? But how am I going to do that? Well, it means I first have to find the equation of the tangent line. Okay? What is the slope of the tangent line? Thinking of a word here. It's the derivative of my original function, isn't it? Oh, okay. So if this is my original function, what's the derivative? Tell me what the derivative, figure it out real
Half
quick.
x to the power of negative half.
Okay, so how about if I write it like this? Would that work?
Yeah.
So for every value on that curve, the slope of the tangent line would be this. Now, I don't want to use 16.1 in my calculations. I'd rather use 16. I have a formal name for the 16. We're going to call it, our starting point is 16. I like to formally call this the happy point. You have to have a happy point. The happy point is the one that's going to be easy to work with, and then you're moving slightly off your happy point, and that's what you're going to give an answer to. But you're going to do your calculations with the happy point. So I'm going to use the y value on the curve to start with. That's easy, square root of 16. And I'm going to use the slope of the tangent line at there. That's easy. I'm using 16 for my x. You with me? Now, how do you find the equation of a line in general? Well, if we use our point slope formula, let me do it over here. The point slope formula, remember, says y minus y coordinate equals slope x minus x coordinate. So in this problem, that's 16. That's the square root of 16. That's f prime of 16. It's the slope of the tangent line. So let's go back over to here. What is f of 16?
4,
4. What is f prime of 16?
1, 8.
1/8, okay. And what is my incremental change in x, which I said delta x and dx are the same value. How far did I move from 16?
0.1.
0.1. These are the only values I need to complete this problem. Now, the reason our estimation is going to be pretty good in the end, I'm telling you now, is because this value is really small. Do you agree that the tangent line has only left the curve a tiny bit? What if I asked you to do the square root of 18, starting at 16? That's a big separation now, isn't it? Because I moved a real long ways. That probably wouldn't be very good, but I expect this one to be really good because I barely moved away, okay? So if I've got this, I'm replacing x with 16.1 at some point, which means this quantity x minus x, that is the actual change on the tangent line. That is my dx. So that means that y equals the square root of 16 plus f prime of 16 times my dx. Okay? And what is this? This is, okay, what is this value right here? This is the answer to the question. This is my change. So when we do that, that means this guy here is my dy, because that's my square root of 16. So the way we say it, we go back to here, this is f prime of 16 dx. And what's f prime of 16? You said it was 1/8. What's dx? So that would be technically 1/80th.
Yep.
So we'll formally write the answer. Here's how we write it. The square root of 16.1 is equal to the square root of 16 plus the actual change in y, which we have no idea because we have no form of technology. You're laughing at that. Remember, this was done for hundreds of years without technology. That's being estimated by the square root of 16 plus this. Well, that's 4. That's 0.125.
0.012.
So that's 0.0125. So this is 4.0125. Without using any form of technology, I'm going to claim that I'm going to give an estimation of the square root of 16.1 without using any technology. Now, we have technology in front of us. Let's cheat. Pull out your calculator.
It's only off by 1.
Let's actually calculate the square root of 16.1. This would be an approximation because it's an infinite non-repeating decimal sequence. How good is our answer here? Well, let's see, the actual square root, that's not even close, right? It's 4.012480553 forever and ever and ever. Huh. If I asked you to give me a 4 decimal place approximation, well, by the way, 4 decimals is a lot of decimals. I want you to give me a 4 decimal place approximation of the square root of 16.1. What would you say? 4.012.
5.
So is our crude estimation fairly good?
Yes.
Mm-hmm.
Or is it like really incredible? Yeah, it's really incredible. Our crude 4 decimal place estimation that we didn't use any technology gave us essentially the same answers our calculator did. Why are they so ridiculously close? Because I barely left the curve because this is really small. The bigger the change would be, the farther away my estimation would be. This would still be valid. It just wouldn't be as good. You with me on this? So this is what is called tangent line estimations. It's also referred to as differentials. Most textbooks just call this chapter this section differentials. The differentials are the dx and the dy terms. Okay, it's an odd vocabulary word. So let me see if I can now set this up formally. There is actually a formula that we have just derived. I used specifics. Let's now be general. All right? I want to do the calculation of f of happy number plus small change. So in our problem, our happy number was 16, our small change was 0.1. You always want to do the calculations of the happy number. I know absolutely, this isn't calculus, I know absolutely this is that plus the actual change in y. That's what this tells me. Our problem is we may not be able to calculate this because we might not have technology in our hands at the time. Or the problem can actually be quite complicated in general. This is going to be estimated by f of the happy number plus dy. But what's dy? It's f prime of happy number times the small change. This is the formula we just derived. This always works, and it's unbelievable how powerful it is if dx, change in, if that's small. Okay? Let's estimate, how about 3.98 to the 5th power. Now, you don't have a calculator. Could you do this by hand?
Yes.
Yeah, do you want to do this by hand? I have a sign-up sheet for everybody who wants to do this by hand. 3.98 times 3.98 times 3.98. Are we in agreement that nobody wants to do this by hand? Okay, good, because I don't want to do this by hand. This is a long 10 decimal place number. We could do it, we don't want to do it. So I need to choose a function. In the last problem, I asked you to do a square root of something, and we chose our function to be the square root function. What do you think we should choose as our function here?
X to the 5th.
Beautiful. How about x to the 5th? Then what does that make my happy point?
4.
Do I want to go 4 or 3?
4.
Why 4?
Less.
Because it's much,
Smaller.
not small, it's much closer.
Closer.
Closer. We want the change to be small. Could I use 3? Yeah, but then my dx would be huge. No, I want to use 4 because there's only a tiny change. It really should never be ambiguous. Okay? Everybody cool with that so far? What is my change then? By the way, delta x and dx are the same. It doesn't matter which way you write it.
0.02.
Are you sure? What are you adding to 4 to get to 3.98? Negative 0.02. Ooh, yeah, that does matter. If I use positive 0.02, then I'm actually working with 4.02. I want to work with 4 minus 0.02. So I need a negative here. Okay? Lastly, what's f prime of x? 5 times x to the 4th. We need to do a couple calculations, but the only calculations we need to do, we need to evaluate our function and our derivative where? At 4. Not 3.98, no. At 4, at the happy number. The number we can easily get. All right, so let's do that. What is f of 4? Okay, 1024. What's f prime of 4? It's nice if you have calculators.
1280.
1280. Do we have everything we need to answer the question? Yes, we do. I can then say 3.98 to the 5th power is equal to 4 to the 5th power plus the change in y. I don't know what the change of y is, so I'm going to estimate that with 4 to the 5th power plus this times this. Just like the last problem. Plus 1280 times negative 0.02. Let's do that calculation now. That's awful too. Try that one more time. Okay. Anybody have a number?
25.6, or negative 25. Or the,
You have to
the
do
second
that.
one.
No, the whole thing. I want the whole thing.
Oh, the whole thing.
Yeah.
1,000.
What do you got?
998.4.
998.4. Oops, 998.4. So what did we just say? We are not, the squiggle doesn't go here. We're not estimating this number. We're calculating this number. We're estimating this. Put an equal sign here, because if I said 3 plus 4, you don't say I'm estimating that with 7. You'd say that's 7, but 7 might be my estimation. So when we finally write the answer, it's good form to write it like this. This is what we just said. Now, I'm pretty sure I did this right. Let's move on to the next thing. Can I check? How? Let's actually calculate this. We can. What is, I'm putting parentheses, what is 3.98 if I raise it to
998.654.
Well, it's actually more decimals, but it's 998.665,47232.
Here's on and on and on.
Actually, it's 23195. I have a trick to get more decimals. One, how many do we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, and one more. Okay, hold on. There's one more thing I can do. This is actually 4/8. I have a cheap calculator, but I can go as many decimals. I know how to play with the calculator. Okay, how do I know it stops there? Because a two decimal place number to the 5th power has 10 decimals. Do we care about these ones? No. How good is my estimation?
Pretty close.
How far am I off by?
0.2.
About 0.25. I'm off by about a quarter. Well, in the last one, we weren't off till the 4th decimal place. Why is this one so far off? Is it far off?
It's not that far.
I'm off by 0.25, but look at the size of my number. It's almost 1,000. The other one, the answer was 4 point something. So think digits. My answer was 4 point something, so I was off in about the 4th, 5th digit. This is actually really similar. Now, this brings us to the next thing. This is a really good estimation. We should be happy with that. All right, so on the job today, Max was off by 20 centimeters on his job. Chase was off by 10 centimeters on his job. Who had a better day? Sounds like a trick question, doesn't it? Okay, well, Max, he's the foreman for the building of the skyscraper downtown, and he was putting a 300-meter beam across the top, and the end of your beam was off by 20 centimeters. Your 300-meter beam was off by 20 centimeters. Chase was performing open heart surgery today and was off by 10 centimeters, which is about the size of a human heart, thereby killing your patient, because you were off by, you might as well have been off by 100 miles.
Good job, Chase.
You understand? So who was closer, the 20 centimeter error or the 10 centimeter error? The 20. This is what is referred to as relative error. See, it's deceiving if I only tell you how much I'm off, because how much I'm off related to, you were off by 20 centimeters over 300 meters. That's microscopic. You were off by 10 centimeters divided by 10 centimeters. You're off by 100%. You see what I'm getting at? So relative error is actually a very common way to describe error. Okay? I have to know the amount that I'm off, but I also have to know what it was supposed to be, and then I can give an answer in terms of percent. All rates are ratios. So we know derivatives are always a rate of change. Now, if it's the slope of a tangent line, it's whatever the y units are over whatever the x units are. But in general, it's a rate of change. A percent is the same thing, but it's a rate of change of things of the same units. So if you went 100 miles on 4 gallons of gas, you'd say you're getting 25 miles per gallon. You drove 100 miles of your 200-mile trip. You drove 100 over 200, or 50% of your trip. Same thing, but those units would have canceled, because that's a rate of the same units. That's now a relative rate, okay? Is everybody so far so good? We want to do a relative rate of change. So I like using geometric examples for this because they're fairly easy to understand. So we have a company, we make cubes. Cubes are us. That's our name. We make cubes of all sizes. We make little sugar cubes. We make those pods that people put in their driveway and then they stay there. Am I right? They stay there forever. They never leave. They were supposed to be temporary, and 5 years later that. Anyway, we make those things. We make cubes of all sizes. Is it possible that everything you make is absolute perfection? Everything's exactly what it's supposed to be all the time, or is that hardly ever the case?
No.
Yeah, there can be a little bit of gimme here. How many have ever bought IKEA furniture? By the way, I love IKEA. I'm not trashing IKEA. So you're going to put together your IKEA furniture and you're looking for the instruction manual. There's no words, it's just pictures. So you're putting everything together and you have the part that's supposed to go like this and everything always fits perfectly. Is it possible that sometimes it won't fit perfectly? Is it possible that one of the things doesn't fit into the hole because the holes were drilled slightly off? Is that possible? Yeah, it can happen. You take it back. More likely, it might be a tight squeeze, but you can get it in. You had a little bit of play. It's called tolerance. You had a little bit of play you could be off by. But there's a point when you can't be off by any more than that, or things just won't fit. But things are not going to be perfect if they're being constructed, even if by a machine. Your errors might be very small, but there's always going to be an error. You'd love it if it was perfect, okay? But that's not always the case. So let's say when we make these, it's a cube, so it's an X by X by X shape, and I'm considering the volume, which would be simply that. Let's say the measurement of any of my edges, okay, each edge can be off a maximum of 1%. If it makes it easy, put numbers in. I have a cube that's supposed to be 100 centimeters by 100 centimeters by 100 centimeters. And each edge could be off by as much as 1 centimeter. So each edge could be anywhere from 99 to 101. Does that make sense? By the way, could it be right on too? Sure, anything in between. That's the most it can ever be off. This is what we have determined when we make our cubes. So that tiny sugar cube, you won't hardly notice, right? It's so small. But I want to know if each edge could be off by as much as 1%, then what is the maximum error the volume could be off by? Well, starting point, it would seem reasonable to say 1%, maybe. So let's find or estimate the maximum relative error in volume. And I'll explain how we do that. Now, if I was doing this without calculus, this would be mind-numbingly long and painful and require a lot of computer time. What I'd actually have to do is what are called a series of iterations. Let's just say hypothetically, you're going to say, all right, let me feed into the computer every possible dimension, starting at 99 by 99 by 99 and ending at 101, 101, 101, and then I'll increment each edge by, let's say, 1/1000th. So I'll count by 0.01s. That means I'm going to do 2001 measurements for each side independently of each other and then multiply them. That's over 8 billion calculations. And that's if I only want to go 3 decimals. If I want to go more, it's more. Can you imagine doing 8 billion separate calculations? Now what you do is you take the most extreme highs and lows and essentially average them together and say, average my error together. Now, that's without using calculus. I'm using an example where there's one independent variable. In Calc 3, we did this today. We use multiple. That 8 billion calculations now starts becoming 10 to the 10 billion calculations. In other words, the supercomputer at UCSD, I can come up with a problem that would take it 1,000 years to do that we can do like in a minute. I'd rather do that one. You can't do it iteratively. It would take forever, and you can't come up with every possible value, can you? Aren't there an infinite number of values you'd have to consider for each side? Yikes. No. So we're going to do it using what we just did. Now, here's the thing. Does it matter if I'm high or low? How many have ever operated a cash register? You were a checker. Okay, I was a checker way back when. Back in the day when we actually had to count back the change because it wasn't, computer, all that stuff. So Every good cashier knows the only thing that matters at the end of the day. I don't care if you did $1 million of business. What's the only thing you care about at the end of the day? That you...
You're within that range.
Not a range. Oh, no, no, no.
They expect you beyond.
No, no, you. Not your job.
Your money's the same as when you started.
And that's called balancing. The only thing that any cashier matters is, did I balance or not? You did $1 million of business and you were off by a nickel. Are you happy? No, you're off by a nickel. I want to be perfect. You know, any good cashier says, no, I want to be exactly right. Now, can you be off by a little? Sure, it's really hard to be exactly right. But you want to be off. So if you were off by a nickel, does anybody care in what direction you were off? No. If you had too much or too little, you're still off. And by the way, if you have too much, you get in far more trouble than if you have too little. I was a checker, I saw 2 people arrested for having too much. Because that means you're cheating. That means you're not entering the dollar amount. You're entering probably 1 decimal place off. So the $100, you're entering 10 and trying to keep track of how much overage because you're skimming at the end of the day. In other words, if you have too much, it means you've been stealing from them because you're undercharging, but you couldn't keep track of how much. If you're too little, it means you're just really bad with money. Either way, that's not good. So it's not about which direction. I'm going to throw darts at a bullseye. I said, oh, I was off by an inch. You said, well, yeah, but is it an inch to the left or an inch to the right? You said, well, was it an inch too high or an inch too low? Does anybody care? I'm off by an inch. Does direction matter? No, only how much. So if I say we're off by as much as 1%, it doesn't matter what direction. I'm off by as much as 1%. So we think of this kind of like an absolute value. So we're saying as much as 1% in either direction. So don't worry about signs, just say it's in any other direction. So now how do I set this problem up? Well, I need a derivative. What is dv dx?
3x squared.
3x squared. This is not a related rate. There's no dt in here. It's just, so here's what I want. I want the actual change in volume over the volume. This gives me relative error. This would be centimeters cubed over centimeters cubed. Now it would be a percent problem. We like those types of problems because I don't have to do as much. We're going to estimate this with the incremental change. This is just like what we did, except now we're doing it as a quotient. Okay? Let's keep going here. I need to figure out what is dv. So going back to here, when we did dy earlier, do I still have it up there? What was dy? It was the derivative times the incremental change. So dv is going to be the same thing. dv is going to be the derivative, 3x squared, times the incremental change. And what is v?
Plus or minus zero.
No, what's v? X cubed. Okay, let's stop here for a moment. This is what I'm going to calculate. You see all sorts of stuff canceling, don't you? Now, let's go back to this statement. Tell me, what does this statement right there mean? If each edge can be off by as much as 1%, is 1% a distance?
No.
No, it's a ratio. 1% doesn't have units. Oh, so what's 1%? It means that dx is at most 1% of what x is. Or another way of saying that is that dx over x is at most 1%. If I said you're putting money into your account and getting 5% interest, 5% isn't a dollar amount. It's 5% of what you put in. You got that? So if the maximum error in the edge, which is x, is at most 1%, that's the error. It's at most 1% of what it was supposed to be. Or I can write it like that. Okay? So I didn't give you any numbers. But you know, small cube, big cube actually won't matter. When I simplify this, what do I get? 3 times dx over x. But dx over x is
0.01.
and there's your answer. If each edge of the cube can be off by as much as 1%, then the maximum error in my volume can be as much as 3%. Does that mean it's going to be off by that much? No, I've given you the upper limit. High or low doesn't matter. You like that calculation? Yeah, it's better than doing the iterative technique where I have to use a computer and bazillions of calculations, and I'm gonna get the same answer, by the way, even if I do it that way.
Doesn't this also appear in statistics at some point?
I'm sorry,
Doesn't this also appear in statistics at some point?
not this version, because that's, in statistics, we do the same concepts overall, but we can't, in Math 119, we can't use the calculus. In upper level statistics, that's calculus based, you can use the calculus. And yes, and then you do things like this. Yeah. Yeah.
Would you say since it's value of 1 being off by 3%, that's like 1% per dimension technically?
In this case, hold that thought for a second, hold that thought.
Okay.
This is true regardless of what percentage I gave you. So if I said each edge was off by as much as 2%, you were still multiplying by the 3, so you're absolutely correct. By the way, I'll give you a hint. If I had said the maximum error in surface area, it would have ended up being 2%. And that's a good catch. It actually really has to do with dimension, but it also has to do with the shape. If I was doing this for, let's say, a sphere or a different shape, it may or may not work the same. I still have to do this, but it's kind of cool. Now, here's the thing. 1% off, whatever it is you're doing, you could live with 1% off, but maybe 3% is too much, depending on what it is you're doing. I'll use this statistical example for a moment. In statistics, the most important thing we study is something called variance. A lot of people think it's the mean. No. Mean is low-level, trivial stuff. Does anyone here have a restaurant or a coffee shop or anything that you frequent on a regular basis? Only one person? Okay. There are people out there that, okay, you go, give me an example of someplace.
Swami's Cafe.
Okay, so when you go there, and let's say you order the same thing, do you want it to be different each time you go, or do you want it to be exactly the same each time you go?
Pretty much the same.
When you guys go to Starbucks and you order something, do you want it to be different, or do you want it to be exactly the same if you're ordering the same thing? Yeah, if you're going to a restaurant or a coffee shop or anywhere, you want the consistency. Now, if I'm going to a fast food place, I already know the quality is not going to be a high level. Think of the quality as being the mean. We have complete control over the level of quality because it's how cheap is it. And if I'm buying a cheap thing, I'm not expecting high quality. But what I do want is consistency. I want it to be the same every time I go. The quality shouldn't change. Now, if I'm spending a lot of money, I'm expecting high quality, but I want it to be the same each time I go. Are you with me on this? The mean is a measure of the quality. We have complete control over that. The variance is a measure of the consistency. And that's the one thing that's totally intolerable, is that you do the same thing and it's different each time, even though you're ordering the same thing. You do not want, this meal was great, and then the next time they burned it, and the next time I got something tiny. I ordered the same thing. So variance is a numerical measurement of consistency, is really what it comes down to. We are doing the same thing here, but we're doing it at a different way, but the higher level, we only have the one variable. So let's suppose that 3% off is too much. The 1% seemed okay. I would need to do the calculation and say, oh, 3%. Now I'm going to give you some reasons why this is so important in real life. Okay, I practically live at Sprouts. I go there at least twice a week. I'm going there as soon as I'm done today. Fruits and vegetables and meat, I buy tons and tons of things. So let's say I want to buy that 10-pound bag of potatoes. Is there any possibility the 10-pound bag of potatoes actually weighs 10 pounds? Now think about this logically. Is it possible? No, why not?
There's no potatoes.
Because the potatoes are all whole potatoes. There's no partial potato. I'm at 9 3/4, I need to slice a piece off of this. No, you're never going to get 10 because the random collection of potatoes are never going to add up to an integer. So what I do is I grab a couple bags and I put them on the scale. I buy the one that's 10.5 pounds. I don't buy the one that's 9.5 pounds. I mean, kind of common sense. But you go to the grocery store and you're buying that bag of potato chips and it says 14.6 ounces on the bag. And you open up the bag, right? Hello, 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 hello. And the echo, because you're looking and it says some settling may occur and you're saying, I don't think I got everything here. And you go and weigh it and it's way short. In the United States, by law, if you are short of that the thing you bought, the product, has to either be replaced or refunded. There is no other alternative. They cannot say no. There's something called the Department of Weights and Measures, and they're really, really nasty when it comes to things like this. If you are shorted and they don't replace it, the fine is enough to close the business. They're going to replace it. You go to a restaurant, you order the 16-ounce steak, and it's this big when you get it. They have to replace it or refund your money. They can't charge you. Not in the United States. That's an absolute, there's no gray area there, and every business knows this. So shorting you is going to cost them a lot more money because they have to replace it. So what's the alternative? Give you too much? Now you're giving it away for free. By the way, it's a lose-lose, isn't it? So in a perfect world, what would I want my variance to be?
The one I give you.
0. Is that possible in reality? That when you're producing products, there's no change in the product whatsoever? No, but you'd want the amount of change to be as small as possible, because if I'm buying that thing and it's a tiny bit short, am I going to complain if it's a tiny bit off? No. If I'm selling and I give you a tiny bit extra, it's not going to hurt me much. It's the bigger variation that's going to hurt me. Now, you guys wouldn't know this, but you might know some disreputable snipes who, travel south of the border, and they'll buy beverages, usually sold 6 at a time, usually named after the sun or something like that. And, you might know somebody who's done this before. And they hold their 6 bottles, 6 12-ounce bottles up, and you notice that every single bottle is filled to a different height. How many have heard of this thing happening? Not that you would know, but you've heard of this. Every single bottle, no matter how many you look at, everyone's filled to a different height. Now, if I dumped all the bottles out and averaged them out, they will come out to be 12 ounces. There wasn't a single bottle that was 12 ounces, but the average will be 12. But the variance is tremendous because the bottling plant is so old and archaic that it needs to be replaced, but that costs a lot of money. So in real life, when the variance gets too big, you have to replace the equipment. Because again, you're going to lose too much money at both ends. So one of the ways we're doing a simple calculation here, if these are off by as much as 1%, we might be able to live with 1%, but we might not be able to live with 3 overall because it is a 3-dimensional object that I'm doing. So what I'd have to do is go back and fix my equipment to make sure that this was smaller. So I'm giving you an example of relative error, and this is actually how simple it is. One of the things we like about relative error, did I have to tell you how big the cube was? No, so this was true for every size cube if I'm using this as the only piece of information. All of my cubes behave the same way. They're all off by as much as that. Now, is it possible it's perfect? Is it possible it came out perfect? Sure. But I'm looking for the most it could be off in that case. And that's what we're saying here. The most it could be off is this, therefore the most this could be off is this. And it's a powerful calculation. So this is using the tangent line essentially to do an estimation. So the first thing we did was to actually physically estimate a quantity. So we gave a numerical value. If we were doing this geometrically, we would give units if units were appropriate. In this case, I'm asking you for relative error. So there would be no units. In the Calc 3 today, we did problems of this nature. In some cases, I asked for the maximum error in volume, and so it was something cubic centimeters. And then later, I asked them for relative error. The cubic centimeters would cancel, and now it's unitless. Now it's a percent answer. So if you said the answer to this was 0.3 or 3%, you're saying the same thing. In fact, most of us would probably prefer that because it's more intuitive, isn't it? I'm off by as much as, and in either direction. Okay, so this is a powerful but not complicated application. Okay, I'm going to go over some stuff that you may have some background in, you don't need to, but I'm going to start from scratch. I'm going to make sure everybody understands the details because the development of what we're going to do next, it's not the most important thing in the calculus, but it is something you're going to use in future semesters, particularly when you get to Math 255, differential equations, and you want to know that you've seen it, had some background. The one thing you do not want to do is to learn something at a higher level that you should have been exposed to at least once, if not multiple times earlier, because it's so much harder when you're learning something down the road that everyone else already has. And all of us will have this happen at some point with something. So we're going to start from the beginning. Okay? The square root of -1. Can this be calculated?
No.
No. Good. It's defined to be what? I. It's defined, and this is the formal mathematical symbol. And I used this at the beginning of the course when I defined sine and cosine, if you remember. Sine and cosine are defined as the positions on the unit circle. The nice thing about this is you can't question it. This is what it is. You can't calculate the square root of -1. It's defined to be I for imaginary. So what if I had the square root of -4 then? Well, it is a square root, and I know the root of a product is the product of the roots. So could I correctly say this?
Yes.
And then this would equal 2i. So this is how you calculate. By starting with the definition, I can do this calculation, okay? So that makes it fairly simple from that standpoint. So that's what an imaginary number is. Now, when we talk about the number groups, okay, this is really important. You learn some of this stuff as little kids in math, but then you don't touch it again for a long time until really you get to linear algebra, then you go back through everything. But there's a whole bunch of things you can do in algebra, and we know what they are, right? There are 11 algebraic properties when I'm solving something. Think of things like commutativity, associativity, identity, inverse. I can use the distributive property. But the most important one is called closure. And when you're in Calc 3, you're going to go through this with vectors. If you've done anything with matrices, you will have understood this concept. Closure means if I take any two things from the same set, and I combine them using whatever operation it is you want to do at that time, could be anything you want, the result has to be in that set for the set to be closed. So if I was talking about something as simple as addition, okay, let's go through our number groups, because this is important that we know this. The lowest number group is what we call the counting numbers or the natural numbers, 1, 2, 3, 4, 5, forever, using n. If I throw in the 0, now it becomes the whole numbers. Not a lot of difference, except those include 0. If I consider every positive and negative, those are called the integers, which we use a capital I, but later in life, you're going to use a capital Z. And I always know when we're doing something and you write Z, I'll say, aha, he knows. Usually there's a level. Somewhere Calc 3 or later, all the textbooks and all the classes will stop calling it I, they'll call it Z. And it's kind of like our secret handshake. When you use a Z for integers, for capital Z, then okay, there must be in a higher math class. But for now, we'll use I for integer. If I now consider every conceivable quotient of integers, which is the definition of a fraction, by the way, that's called the set of rational numbers, but we use a Q for quotient. Now, what is a rational number? A rational number is any number that can be written as a fraction, or a rational number has a decimal equivalent. All rational numbers either have a terminating decimal or an infinite repeating decimal sequence. And it doesn't have to be one number, it could be a whole bunch of numbers, but all rational numbers are either terminating or have a repeating sequence forever and ever. And we learned as kids to write bar over the top, right? That makes it easier. So there's one more possibility. Infinite. This is infinite repeating. What's the other possibility?
Irrational.
Infinite
Non-repeating.
non-repeating, good. Square root of 2, pi. Okay, that's what an irrational is. Irrational is infinite decimal, but not repeating, and we usually use IR. Now, every number you can think of is either rational or irrational, and when we put them together, we get the reals. And we've always thought of those as being at the top of the food chain. Nope, they're not the top of the food chain. Because for every real number, if I put an I next to it, I now have created an imaginary number. For every real number, there's 5I, 10, 10I, 1/2 I. Every real number has an imaginary number that goes hand in hand. And we call that set IM, the imaginaries. And now when I put the reals and imaginaries together, that forms the biggest number set. Does anybody know what that one's called?
Complex.
Complex. And that's where we use the script C, like we use the script R for real. The complex numbers are the biggest number set. We tend to not deal with them yet. So right now, this semester, next semester, you are going to master the calculus of 2 dimensions. But you're not only mastering the calculus of 2 dimensions, you're mastering what is called real valued calculus, meaning everything you work with has real input and real output. Calc 3, you're going to master 3-dimensional real valued calculus. Differential equations, you're going to go back to 2 dimensions and you're going to do all the applications that are left. And now you're all done with math. No, now it starts. Now you start your upper division. And one of the first courses many of you will take is a class called complex analysis, which is the calculus of complex numbers. And now you learn everything else, but you have to master 2 dimensions, 3 dimensions, and then real numbers. That's why we do it in progression. You can't do it all at once. It's just too much information. So, if I took any 2 natural numbers and added them together, is it still a natural number? A lot of these you don't have to prove. We assume these. They're called axioms. They're absolute truths that we can't prove. By the way, there are a lot of truths that you cannot prove. I have a point here, I have a point here. How many lines can I draw through these 2 points at the same time? I have 2 points. How many lines can I draw through one? One. That's a really important one. Can you prove it? Actually, no. We accept it as a starting point. It's called an axiom. It's a building block. A theorem is an absolute proof, an absolute truth that you can prove. Axioms and postulates are absolute proofs that we accept as starting points. So we start with these guys in definitions and then build. If I take any two whole numbers and add them, do I always get back a whole number? Integers, rationals. One of the first proofs you learn how to do in discrete math, Math 245, is to prove that the sum of two rationals is also rational. Is an integer a rational number? Is the number 5? I said a rational number is any number that can be represented as a fraction. 5 over 1. In fact, keep going. 10 over 2, 15 over 3, those are all equal to 5. Oh, so that's why all integers are rational, but not all rationals are integers. So if I keep going up, obviously all of these are close to addition. So if I grab any two irrationals, right? If I add any two irrationals together, I always get back an irrational, right? Is 0 rational or irrational? It can't be both. It can only be one. It's rational. I just came up with an example where I added two irrationals and I got back irrational. This set is not closed to addition, and neither is this set. The rest of them are. That's it. 1, 2, 3, 4, 5, 6. Of the infinitely many sets of numbers, there's only 6 that are closed to addition. I can go through the same thing with multiplication, and we'll find the same thing is true. If I take root 2 times root 8, I get 4. If I take any two imaginaries and multiply them, now this is something interesting. What if I took 2i and I multiplied it by 3i? What do I get? I get 6i squared. But if I is the square root of -1, then what's I squared always going to be?
-1.
And that's one of the great confusals. We never write I to a power. We just put what it is. So when you square I, you get back -1, which is just crazy. But it is cool because there's so much math we can do as a result. If you multiply any two imaginary numbers together, you'll always get back a real number because you're always going to get back something with an I squared. So imaginaries fail closure really bad. Okay? So let's keep going. It is common to represent complex numbers by using a small z. So I have two complex numbers here where A, B, C, and D are all elements. A, B, C, and D are real numbers, in other words. So 3 plus 4i, 7 minus 6i. The numbers are all real, but I threw an I at the end. So these are complex numbers. Let's call that Z1 and Z2. So Z1 and Z2 are elements of the complex numbers. I want to add and I want to multiply these two things here, because I want to determine if the complex numbers are closed to addition and to multiplication. So what is Z1 plus Z2? Well, that would be A plus B, I plus C plus DI, and this is addition, and addition is commutative, and it is associative, so I can rearrange and I can regroup. So could I write it like this?
Yeah.
Is that legal?
Yeah.
In fact, that's exactly what I would want to do. Let's do an example. Z1 is 4 minus 6i. Z2 is 8 plus 3i. What is Z1 plus Z2? Well, it looks like I'm just going to add the reals together. And then I'm going to add the imaginaries together because I just have to add their coefficients. Oh, okay, that was easy enough. So adding complex numbers, pretty trivial. I want to multiply these guys. If those were variables, this would be a baby algebra problem, right? What's the acronym we would call? FOIL, right? You'd multiply this out. So what would I get? AC plus ADI plus BCI plus ADI squared. Now, tell me about that guy.
Negative
Isn't that just negative AD
Yeah.
because of the I squared? So if I put this back together, sorry, I got it. Yeah, sorry, BD, sorry. Can't read my own writing here. AC minus BD plus AD plus BCI. Is this a real number right here?
Yes.
Is this coefficient a real number?
No. Well, the coefficient, yes. Yes.
So is this the form of a complex number in the end?
Yeah.
So we have just proven that complex numbers are close to multiplication. If you multiply two complex numbers, you get back a complex number. Now, I'm going to go out on a limb here and say that anything you can possibly write that's a number is complex. Wait a minute. I'm going to take the number 4. I'm going to take the number 3i. And you're telling me both of these are complex numbers? A complex number is any number that can be written in this form. Can you write the number 4 in that form? Yeah. 4 plus 0i. Ah, then what's this guy?
0 plus 3i.
Did I do it? Yeah. Real numbers are complex with 0 imaginary part. Imaginary numbers are complex with 0 real part. So what we often make the distinction of, if I say real number, there's no ambiguity. If I say imaginary number, there's no ambiguity. When I say complex, you say, well, it could be purely real, it could be purely imaginary. So what we err on the side of, whenever we use the term complex, we're really referring to things that look like this, have real and imaginary part. Knowing I could get something different, but we really want to think of them as both being there. Okay? See with me so far? So that stuff's pretty simple so far. Now, this is way back, a million years ago algebra. So now let's go to the next level of stuff. I know on the unit circle how to represent things rather simply, okay? We know that that's cos theta sine theta, am I correct? We know that's the definition of the x and y, it's the sine and the cosine, okay? I'm going to define, keep that in the back of our mind, we're going to use that in a moment. I'm going to define something to you that's going to be a little bit, blow your mind a little bit, but I'm giving you a glimpse. This is mathematics. In a perfect world, you were exposed to this in both trig and pre-calculus. In reality, a lot of you may not have been exposed to it in either one. It's part of the curriculum, but not everybody gets to see it all. All right. This is the real axis. This is the imaginary axis. This is what is called the complex plane. This is actually the way things are. This is the way things have always been. The math you have done in most of your life lived on this axis. All the algebra you did lived on this axis. All the calculus you did lived on this axis. You only dealt with real numbers, positive or negative. I'm going to open it up to you. This is the complex plane, and here's how we represent it. There's a point right here. We'll call the point A, comma, B. A units in this direction, obviously B units up. Every ordered pair on the complex plane represents a complex number. So this is representing the number A plus BI. That means since every possible ordered pair I could draw would give me every possible real first number and then every possible imaginary second number, every complex number can be represented as a point on this plane, can it? There's no thing you cannot, right? A plus BI, every possible A, every possible B. Every point on this plane is represented, but I can see the plane. The plane's not confusing. So let's call this Z again, like we did before. That's A, that's B. A and B are real numbers. I went A this way, I went B this way. Everybody okay with that? That's pretty safe. Can't I just use Pythagorean theorem here? Yeah? What is this? Yeah, and A and B are real, that's no problem. So we have a name for this. We call this, now, in trig and pre-calc, you guys remember hearing the term modulus? How many remember hearing that word? You were told the modulus of a complex number is that number. And you say, but you're using an absolute value symbol. Is it the same thing? And what did your teacher tell you? Oh no. That was a lie from the pit of hell. This is the definition of absolute value. It is absolute value. The word modulus is made up. Never use it again because you're probably going to misinterpret. Modulus is a made up term. This is absolute value. And that's why we use an absolute value symbol. What does the word absolute value mean to most people? Think number line. Keep it simple.
How far away it is from 0?
Perfect answer. Here's 0, here's the number 6, here's the number -6. How far is 6 from 0? 6. How far is -6 from 0? 6. So we'd say the absolute value of -6 equals the absolute value of +6. They're both 6. They're how far am I from 0? It's like, duh. The complex plane. What is this ordered pair? Isn't it 0, 0, which would be 0 plus 0i, or simply the number 0. And how far is this point from 0? This far. That's what absolute value is. You've just done absolute value with real numbers only. You had no imaginary part. Absolute value is still defined as how far is a number from 0, but not necessarily on the number line. Now, a number line is correct when I'm only dealing with real numbers. What if I was dealing with a purely imaginary number? Then wouldn't I, 8i, -8i would still be 8 units. It would still be that distance, but now that I'm out here and I have real and imaginary, I think Pythagorean theorem. So that modulus of the complex number is the absolute value of the complex number. That is actually the exact same thing. And if you think back to where you've dealt with absolute values before, now when you're a little kid, you always do absolute values of numbers. The calculus student sometimes has to do this one. Now, most people think of this as a better definition in the real number world. So x is a real number. What is the square root of x squared? Do you remember? The absolute value of x. If x is negative and I square it and take the square root, don't I get back the positive version? Oh, so we know this. Oh yeah, this is exactly what I did, right? This is what most people think of definition of absolute value. This is a good one if it's purely real. What's the difference between this and what I just did? We have an imaginary part. See, in the real system, that number is a 0. So this is the square root of a squared, which is absolute value of a, because a could be on either side. So it absolutely confirms what we already know if I choose the b to be 0. But now we've changed it a little bit. Isn't that crazy? So this is what absolute value is. It's how far am I from 0, even in this situation. Now I'm going to define something. If z equals a plus bi, we're going to define, and we actually say z bar. We say it that way. That's z bar. Z bar is defined to be this guy. There's a word. It has to do with conjugate, but not like the usual conjugate you're thinking of. Usually when we think of a conjugate, we're thinking of the real part conjugating. I'm not conjugating the real part, I'm conjugating the real and the imaginary. So we call these guys complex conjugates. And they are extremely important because when I take z and I multiply it by z bar, I get a plus bi times a minus bi. Now, multiply that up for me, will you? Tell me what you get. Go all the way out to the end. Don't, whenever you multiply conjugates, don't you get a difference to squares? So what are you going to get in this case?
A squared minus, no, a squared plus.
A squared plus b squared.
Crazy.
Oh, I multiply two complex conjugates, I get a sum of squares, and that's real, by the way. Baby algebra, you're supposed to factor this. Baby algebra, what are you always told? Well, first of all, you're told it's prime. You're told that can't be factored, and that's actually always the wrong answer. There is no real factorization of this. Anything you write down, anything you write down can be factored. Absolutely, there's no such, prime is a made-up word. Prime is when you don't have integer coefficients. Get rid of that word. Can this be factored? Yeah. But it's a complex factorization. Oh, I did factor it. Now, is it a useful factorization if we're living in the real world? No. Because my roots are both imaginary. But this is a correct factorization. If you multiply anything by its complex conjugate, you will get a sum of squares. So the magnitude of this, if I square it, is equal to z bar, isn't it? Ah, that's actually a useful thing. Now, I got all this stuff. I'm messing around with the algebra. There's a whole bunch of different things going on that you may have done in pre-calculus, like de Moivre's theorem and finding all the roots of things. There's a lot of cool stuff. We're not interested in that stuff. We're interested in now going back to here. All right? I'm going back to this picture, and now we're on the complex plane. So this represents on the complex plane cos theta plus sine theta I. Now we're on the complex plane. But I still want that 1. If I said what's a squared plus b squared, wouldn't it be cos squared plus sine squared? Which is equal to 1, which matches that picture. Now, you usually don't see the I after the theta. I'm sure all of you have seen some version of that before, but where do we typically put the I? In front of the sine theta, which, by the way, you would never write this, 4 plus I3. You don't write that, you'd write 4 plus 3I. It's this problem. Is this sine of x times y, or is this the sine of xy? You see the basic problem when I write it that way. It's a little bit ambiguous. Is this the sine of theta I? Or is it the sine of theta? Yeah, so the reason we put the I in front is so that people don't confuse those two together. And you're saying, who the heck's ever going to confuse an imaginary angle? When would you ever use an imaginary angle? You've used an imaginary angle every time you've ever done math in your entire life. You just didn't realize it. Yeah, most everything you've ever done in your entire life mathematically, you have been using imaginary angles. Hate to tell you. You're going to see today, you've been using imaginary numbers all over the place and you didn't realize it because you were getting the final results. You didn't see the process. Yeah, theta I we're going to be doing today. We're going to be doing angles that are imaginary today. But right now, I want my angle to be theta, so we often write it this way just so there's no possibility of ambiguity. If it's this, we put the y in front, so there's no possibility of ambiguity because I don't feel like using parentheses. It would be correct, but I don't feel like it. Okay, now, let's stare at this for a moment. That means that every complex number I can break down into this form. I can do sine and cosine. So I'm going to do an example of one. Let's suppose the complex number I'm dealing with today, we'll go really simple. Let's say it's 2 plus 2i. I would like to break it down and write it in this sort of form. But how would I do that? Well, first off, is that the correct representation on the complex plane? Can you tell me what this angle is?
Oh.
It's a slope of 1, so the angle would be 45 or pi over 4. I'll write pi over 4. And what's this length here?
Z?
Oh, what is it?
No.
Would be the square root of 8?
Yeah, 2 root 2.
Or 2 root 2? Stare at this for a moment. Tell me if you believe this. Is that the same thing?
Unfortunately, yes.
Yeah, this is called the polar or trigonometric form of the complex number, which is actually far more useful most of the time. The polar or trigonometric form really is useful when you have common angles, by the way. I used 45 degrees. Because that's root 2 over 2 times this gets me back to 2. Root 2 over 2 times this gets me back to 2. But that's the part right there. It's the part that's of length 1 that I need. So all complex numbers ultimately can be written in this form. Every complex number can be written in this trigonometric form. Okay, there's no exception. Okay, you with me so far? So what we do was, we do this. I have something of this form. If I find the magnitude, right, the absolute value, which we just did, we said it was 2 root 2, then it equals the magnitude of z times cosine of the angle plus I sine of the angle. Now, I don't know what the angle is. It depends on the numbers. This is called the standard form. This is called the trigonometric or polar form. They're both valid and depends what your uses are at the time. Okay? But I want to look at this one right here. Arguably the most important formula slash identity in the history of mathematics I'm about to expose you to. I would hope that you'd seen this somewhere else. It's the formula that links real to complex to imaginary, to circles to triangles, to what are called the hyperbolic functions, to logarithmic functions, and to exponential functions. They're all related by one simple formula. Well, we just dealt with that. How many have seen this before? Pre-calc or trig?
Trig.
Not pre-calc.
No, it's trig.
See, I'm glad you saw it trig. I would have hoped you saw it in both. Now, we're going to be working with this today. This formula is huge. It's not hard to use, but boy, does it look weird. Assume for a moment that theta is a real number. Then that means this is an imaginary exponent. Yikes. Yikes. Now, this formula is, I'm telling you how important this formula is. That, okay, I'm a huge sports fan. Most people know that. Before they moved to Tennessee, the Tennessee Titans used to be in Houston. They were named after this. Wayne Gretzky, greatest hockey player of all time, won 4 Stanley Cups and set all his records by playing for this team up in Edmonton. Both of these teams were named after this very, very famous mathematician. This is called who did Wayne Gretzky play for in Edmonton? The Oilers. That's how you pronounce it. That's Oilers formula. I am pretty sure both the Houston Oilers football team and Edmonton Oilers hockey team named their teams after this guy because both their owners were really well-known mathematicians. At least that's what I choose to believe, okay? Euler's formula is so important that we named professional sports franchises after this person. This is arguably the most important formula in all of math because of how many ways it's used and how many identities and formulas and different things we come up with. But on my unit circle, okay, every point on my unit circle can also be represented this way. And one of the great advantages of this is the ease of calculation. If I took a complex number, a plus bi, and I raised it to a large power, would that excite you to do that problem? Let's say we want to raise this, I don't know, this is the 8th power. Do you really want to multiply that out?
No.
I don't want to do that. We could do that. But just a moment ago, we wrote it like this. 2 root 2 pi over 4, sorry. Cos pi over 4 plus I sine pi over 4. Okay, now I'm going to raise that to the 8th power. Did this just get a lot better or maybe even worse? But that's equal to 2 root 2 e to the pi over 4 I to the 8th power. Oh, that's actually pretty simple. 2 root 2 raised to the 8th power. Do that on your calculator real quick. What's 2 root 2 when I raise it to the 8th power? Or just go square root of 8 raised to the 8th power.
4,000.
4,096.
Yeah.
Aren't there rules of exponents right now?
Uh,
This is going to be e to the what?
2 pi I.
E to the 2 pi I. So that's 4,096 times the cosine of 2 pi plus I sine of 2 pi. What's the sine of 2 pi?
1.
Sine of 2 pi?
Sine 0.
0. What's the cosine of 2 pi?
1.
1. So my answer is,
1.
oh. That made that a lot easier, didn't it? Using Euler's formula meant I could take a complex number, raise it to a large power, and all I needed was the angle and the absolute value. Now, again, trig, pre-calc, hopefully you did stuff like this. Do we need this kind of stuff in general for now? No. No, these are just all little factoids of the complex numbers that I want to relate to this formula. Now we're going to define something. We're going to define what are called the hyperbolic functions. And unfortunately, pretty much all of the calculus books written in about the last 40 years have removed all of this. They've removed all of the development, the definitions, everything, and they give you final results. And then when you get to differential equations, all the stuff I'm showing you, you're supposed to know. But you'll say, we didn't do that in my calculus class. How would I have known all this stuff? Because it's not even in the calc books anymore. So we're going to define what are called the hyperbolic functions. Okay? You have a key on your calculator. You have an HYP key. So if just for fun, hit HYP cos. And what does it say on your screen now? It says COSH. That's your way of saying it's hyperbolic cosine. So we call it the hyperbolic cosine of x. That's how we say it. The H means it's hyperbolic. It's not a coefficient. So on your calculator, hopefully all of you have that as a main key. You have an HYP key. That's how you make it a hyperbolic cosine. You hit HYP cos and it says COSH. That's no longer the cosine you did a moment ago. This is defined to be the cosine of IX. Remember a moment ago I said you will be dealing with imaginary angles? If x is a real number, then this is an imaginary angle. Yikes. Is that crazy or what? By the way, we know that a cosine has to range between -1 and 1. Am I correct?
Yes.
Cosine has to range between -1 and 1. I would like you all, let's do, let me do this. Put your calculator, make sure you're in radian mode. Oh, my calculator's getting weird on me. Uh-oh. Oh, here we go. Make sure you're in radian mode for the next thing we're going to do, okay? Sorry, my keys are sticking just a little bit. There we go. All right. I would like you to find for me the cosine of 4i, but don't do it yet. What do we know about sine and cosine? They only return values between -1 and 1, right? Are you sure? Find the cosine of 4i for me. 4 times, your angle is 4i. Your angle is imaginary. And I want you to find the cosine of that. That means you're going to go HYP cos 4.
27.2.
Wait a minute. Didn't we just say cosine has to be between -1 and 1? That was a lie. That's only if your input is real. If you're not limited to real input, then the cosine can return numbers between -infinity and +infinity. It has no bound. Isn't that crazy? But that's if I allow for imaginary input. If I'm doing real input, cosine still stays between -1 and 1.
So then what about for 10, because it already returns?
Well, hold on. We're going to talk about all those. You said this is approximately 27.3.
Yeah.
Yeah.
I just input an imaginary angle and you gave me back a real value. Cosine will return a real value no matter what the input is, by the way. No matter what the input is, cosine will always return a real value. I gotta admit, that's crazy. Now, the hyperbolic sign, I'll put right under. Now, hyperbolic sign generally returns an imaginary answer. Yikes. So, I is a number. It's the square root of -1, but it is a number. It's not a variable. Let me ask you a simple question. I want you to differentiate the sign of constant times x. What are you going to get? K is a constant. What are you going to get? Cosine of constant x times constant. I is still a constant. So I can take derivatives of this without any issues whatsoever. So if I take the derivative of the hyperbolic cosine of I, in other words, the hyperbolic cosine of x is the cosine of ix, what am I going to get? I'm going to get negative I times the sine of ix. Wait a minute, isn't that the hyperbolic sign? So the derivative of hyperbolic cosine is hyperbolic sine. Not negative, it is just straight up hyperbolic sine. Interesting. Let's differentiate the hyperbolic sign, shall we? What are you going to get? You're going to get the cosine of ix. I'm sorry, there should be a negative I here. I'm going to get negative I times the cosine of ix times, what is negative I times I?
1.
Positive 1, because it's the negative of I squared. Now what do you notice? Ooh, this is convenient. The derivative of hyperbolic sine is the hyperbolic cosine, and the derivative of hyperbolic cosine is the hyperbolic sine. No plus or minuses to worry about. I guess that could be a good thing. Okay? Now, we define all of the other hyperbolic functions in the same way as we did the regular ones, meaning the hyperbolic tangent of x is defined to be the quotient of these guys, which ends up making it negative I times the tangent of ix. The hyperbolic secant of x ends up being just the secant of ix. We don't bother with the hyperbolic cotangent or cosecant. They're never going to come up. They really are never going to come up. The derivatives are pretty simple to show. I've got derivatives. I still don't know what these are used for. I don't know how my calculator was able to do the cosine of an imaginary angle. Like, how is all this stuff happening? Well, now we're going to use Euler's formula. I'm going to show you the relationship between the trig functions and the exponential functions, because Euler's formula is an exponential function. Okay, let me take this stuff out here. Alrighty. Going back to Euler's formula, e to the I theta is cos theta plus I sine theta. Okay, great. Let theta equal negative Ix. Then what would I have here? I'd have e to the I times negative Ix. And what's that? That's just e to the x. So I can get e to the x by replacing the theta with an imaginary angle. Isn't that crazy? So that's a crazy relationship, but now I'm going to replace all my thetas with this. So this is the cosine of negative Ix plus I times the sine of negative Ix. Now, remember we talked about odd and even functions? Have we talked about odd and even functions in here? I know, maybe it was the trig class that I subbed. Odd and even functions. This is something that's really powerful in calculus. I'm going to give a quick review of that because we're going to use this property to come up with something. An even function is any function where f of negative x equals f of positive x. Meaning, graphically speaking, the y-axis acts as a mirror image. What kind of functions have this property? Well, x to any even power, right? Like x squared, x to the fourth, cosine and secant have this property, don't they? They are even functions. I know that if I take the cosine of, negative pi over 4, for example, that's the same as the cosine of positive pi over 4. Cosine, secant, and x to any even power, those are examples of even functions. Why is that important? Because what does that mean this is? This is the cosine of ix. Now, what's an odd function? Anybody remember that one? Even function, I have what's called mirror symmetry, right? The y-axis, I see a perfect mirror. An odd function is one that has what we call rotational symmetry. If I take it and spin it 180 degrees, it looks the same. Well, what has that property? Well, x to any odd power. Y equal x cubed, x to the fifth, and so on. But the other 4 trig functions all have that same property, don't they? The sine function, if you flip it 180 degrees, looks the same. The tangent, you flip it 180 degrees, looks the same. But the main property of an odd function is if I take f of negative x, it's the negative of f of x. So if this point here is x f of x, and I go negative, now this is negative x and the negative of f of x, because I flipped over. Odd functions have this property. Sine is an odd function. So the sine of negative ix is the negative of sine of ix. And we have our first humongous result. E to the x is equal to hyperbolic cosine of x plus hyperbolic sine of x. Ooh. As weird as the hyperbolic sine and cosine are, they add up to e to the x. Is that crazy or what? That's a cool thing. You didn't see that one coming. Now we're not done. Now we're going to do the other half of this. By the way, all of the notes are online for this. So if you're like, some of the notes are kind of crazy wild. If you go on in the notes section of modules, you'll see the hyperbolic functions. There are notes for all of this with some examples. Because I'm guessing this part is brand new to everybody. If you've had calculus 4 times and you're taking this, I'm guessing this is still brand new. Why? Because most people who teach calculus, I hate to say it, don't know calculus. This is critical information for the next 3 semesters of math. And most people don't show you this anymore. It's unfortunate, but it's reality. Now I want to replace theta with positive ix. When I replaced it with negative ix, I got all of this. Now I want to replace theta with positive ix and see what happens. So now I would have e to the I times ix. And what would that be? Good, e to the negative x. And that would be the cosine of ix plus I sine of ix. Well, I don't have to do anything clever. That's still hyperbolic cosine. Oh, but wait a minute. That's not hyperbolic sine. That's the negative of hyperbolic sine, isn't it? So can I just write minus hyperbolic sine?
Yeah.
So I have 2 really, really cool and powerful statements that I'm going to put together now. We now have e to the x equals hyperbolic cosine of x plus hyperbolic sine of x. We have e to the negative x equals hyperbolic cosine of x minus hyperbolic sine of x. I would like to write both the hyperbolic sine and hyperbolic cosines in terms of the e to the x's. Well, if I add these 2 together, what will I get? Well, I get this. Yes? No?
Yeah.
That's,
So therefore, would this be a true statement? Would that be true?
yes.
This is how your calculator just calculated the cosine of 4i a moment ago. Your calculator is programmed to do this when you ask it a hyperbolic. This is an alternate version that deals only with real numbers. Way simpler to use. Now, what if I subtract these two? Instead of add, what if I subtracted them? Then what am I going to get? Want to get that? And if I check by derivatives, the derivative of this will still give me this, and the derivative of this will still give me this. Now, this is a more workable version that if I had to actually do calculations. By the way, do all calculators have an HYP key on? Not necessarily. So what if I needed to do the hyperbolic sine or cosine of a number? Well, then I can also do that. Okay? So far, so good? We haven't done any calculus yet, by the way. Well, we did the derivative of sine and cosine. I want to differentiate, oh my gosh, I want to differentiate the hyperbolic cosine of thing. Oh my gosh, how am I going to do this?
Product rule. No, never mind.
Hyperbolic cosine of thing. Hyperbolic sine of thing.
Yeah.
Derivative of thing.
There you go.
That's it?
Oopsies.
That's it? Looks like just a regular trig function, doesn't it?
Sorry, I thought it was like.
How about if we want to do the derivative of the hyperbolic sine of thing?
That's equal to.
Then it's hyperbolic sine of thing, then it's equal to the hyperbolic cosine of thing times the derivative of thing. Well, that's,
You forgot a negative sign for the derivative of cos. Should we do?
no,
No?
there's no negatives. We just derived those a little while ago. No negatives. Oh, well, that seems kind of crazy.
That's gonna be fun.
So I want to differentiate the hyperbolic cosine of, I don't know, x cubed. So what's my answer? The hyperbolic sine of x cubed.
Times derivative of thing, which is 3.
Okay, now what? We're done.
Put thing.
That's it. You don't need to do anything else. You never need to change these to the exponential version, although you can. It just makes them uglier. But that's it. So the derivatives of the hyperbolics are actually pretty simple for the most part. Wow.
So I have a question. So like, if you did e to the x times e to the negative x, would that,
That would be 1,
right, so that is not technically.
but that's not part of this problem.
No, this is unrelated to this. I'm asking like a.
If I did e to the x times e to the negative x, I'd get 1.
Right, and then that would be the cause of.
Oh, you want to multiply these guys?
Yeah.
Oh, this one is one of the craziest formulas of all of them. What is the Pythagorean theorem, right? Sum of the squares of the bases is the square of the hypotenuse. What's the Pythagorean identity for sine and cosine? Cos squared plus sine squared is 1. That doesn't work for the hyperbolics. I like your thinking, CC. If I multiply these guys on the left, I get a 1. If I multiply these guys on the right, aren't those conjugates?
Yeah.
So wouldn't I get hyperbolic cosine squared x minus hyperbolic sine squared x? And that's the hyperbolic Pythagorean theorem. I don't know if I told you guys this or not, but there's a book that I bought a few years ago at Powell's bookstore. Anybody know where Powell's bookstore is? It's one of the biggest, might be the biggest bookstore in the world. It's in Portland. It's literally an entire city block. It's about 4 stories. It is Hogwarts, I think. I've been there many times, and no matter what, I turn around and all the walls have changed. The stairs are in different places. Have you had that experience?
Yes.
They have a lost and found there where the parents are the ones that get lost, and the kids find their parents in lost and found, not the other way around. It's a crazy place. But they have a math room. that's bigger than this room just for the math books. And I get lost in there. And a number of years ago, I found a book. It was called YE equals MC squared, okay, which is the theory of relativity that Einstein came up with. It was written by 2 Cambridge physicists. And in the intro to the book, it says, you don't need any special degrees. You don't need any background to understand. So when you start reading, it's unbelievably fascinating and cool. For example, if I run really, really, really fast, I'm going to age slower than all of you. Now, it might not be much slower because I can't run quite that fast. And if you can show with a pendulum clock that if a train is going by, the time moves slower on the train than you are moving. So one of the things about this book said you don't need to know all this. And then they immediately start the explanation. It's 4-dimensional non-Euclidean hyperbolic geometry. I have multiple degrees, and I think you actually needed a PhD in physics to understand by about the time you got to the second chapter. It was unbelievable. Now, 4-dimensional hyperbolic geometry. Hyperbolic geometry is when you have this, not the sum of squares, but the differences of squares that stay a constant, like a hyperbola in that sense. And it was crazy, 4-dimensional, and so in my Calc 3 where they understand vectors, it's all 4-dimensional stuff. But they treat the speed of light, they call it the universal speed limit, and they never use numbers. And they talk about how much energy is contained in a static object versus, it's really cool, really hard to understand. But that equation right there is sort of the foundation for a lot of the theory of relativity, that one on top, which is crazy. Yeah.
What's cool about Einstein's theory is that if you consider the speed of light being constant, is that being 1, E equals mc squared is not actually complete. There's another part based on how fast your velocity, so basically it's like a vector.
Well, the E equals mc squared, you guys, anybody know any physics? What's energy, generally?
It's
mv squared.
Energy.
Energy is generally calculated mass times the square of velocity. So what's mc squared? C is the symbol we use for speed of light. Oh, so in other words, it's the upper limit. Because you can't, in theory, go faster than speed, unless you're like Star Trek or something. You can't go faster than light speed. Cool stuff. But this is a crazy cool identity because it's backward. But remember, you're talking about imaginary inputs. So bottom line, by the way, you're going to find this out by the time you get to 255. Every time in your life you've ever been dealing with purely real numbers, you were probably dealing with e to the x in some capacity. And every time in your life you were ever dealing with purely imaginary numbers, you were dealing with sines and cosines. Sines and cosines come directly back and forth from imaginary numbers, even though I'm working with real numbers. And when I was dealing with crazy, both, then I was dealing with probably the product of E in sine and E in cosine. We prove this in Math 255. All your life you've been dealing with imaginary numbers. You just didn't realize it because all of these results are for imaginary numbers. We just need to see the final result. If this makes sense to you, then you don't need the imaginary version of it. This is a result of the definitions and Euler's formula. Okay?
One more question. Is this how they got our, what we know so far, which is 1 equals cos squared plus sine squared? Is that how they got it? Did they use this?
No. That's a straight up Pythagorean theorem. Yeah, the real stuff is just simple Pythagorean theorems. That's not complicated. This is crazy complicated. If I asked for the derivative of a hyperbolic function, it's going to be just like the derivative of a trig function. You're going to do the appropriate derivative, and then you're going to have the chain rule factor. This is not complicated. There is one exception, and one exception only. The only time, and by the way, you do not need to change any of these. I do not need to change this to e to the x. That makes it too complicated. The exception would be, because we know this is true now, what if my argument isn't an x, but what if my argument is a logarithm? What if my argument's a logarithm? Then what are you doing? E to the log. This is the one exception where you must change it to exponential. I'm going to walk you through. So I've got the hyperbolic cosine of the natural log function. If I don't change it to the exponential, I'm going to have something that's way too complicated. If I change this to the exponential, then what is it? E to the log x plus e to the negative log x. What's that? What's that?
Minus.
Would you say that derivative is pretty easy to take from here?
Yeah.
Yeah. The only time you've got to change it to the exponential version is if your argument's a logarithm, because the e will undo the log. The rest of the time, you just leave it like this. There's no reason to change it. Now, we're doing all of this stuff. Is there any physical application? Is there any place on planet Earth where you actually see this stuff? Yes. That's what I'm going to show you next. All right. I was watching weird stuff on TV where somebody took a cable and extended it across, these skyscrapers way up in the air, and then you guys ever see crazy people do that? They're walking across the tightrope, like 1,000,000 feet in the air. You're like, whoa, how many have seen something like that? I don't know why people would do that, just nuts. So I decided I want to start practicing, but rather than go to the top of the skyscraper, I'm just going to do it on the 4th floor. So we're going to put a cable and go across from here to the other rail. And I want you to pull it as tight as you can so it's perfectly horizontal. I want you to pull that. I don't care what that cable's made of. It can be made of raw steel. I want you to pull it till it's perfectly horizontal. Do we have a problem with that? Yeah, it violates laws of physics. That's actually not possible. No matter how strong the substance is, it would snap. It's not possible because of the G word. Gravity. I don't care if it's dental floss. You can't make it perfectly taut. Do you guys understand that? There will always be a dip. That shape is called quaternary. I think I'm spelling this right. A quaternary. The shape was called a quaternary. It kind of looks like this. This is the hanging cable. Oh, by the way, while we're at it, the shape is the graph of the hyperbolic cosine. All hanging cables. I don't care if it's solid iron. There's still going to be, even at the subatomic level, a dip because of the gravity. So you can never make anything perfectly horizontal. So if you wanted to describe the dip, depending on how severe the dip is, the more severe the dip, the larger the exponent. So if you were to draw the graph of the hyperbolic cosine, think of it this way. It's the average of these two functions. Oh, the average. So I've got one exponential function doing this, the other exponential function doing this. I want their average. I get this. The hyperbolic sine, not so much. So a quaternary describes a hanging cable. Now, is this important?
Yes.
Is this important when we build things?
Yes.
Oh, yes. This is very important when we build things. How many have ever been to Vegas? You ever stayed at any of the big hotels? Yeah, I've been there many, many, many times. I used to compete in international tournament there every couple of years back in the last millennium. I always found it rather interesting. You're on the bottom floor of a really tall hotel, and literally it's a football field-sized room without a whole lot of pillars or anything else. Right? We would compete on the first floor of these gigantic rooms where there was no pillars, big as a football field. What's keeping the 20th floor from coming down and becoming the first floor? I always found that really interesting structurally. That always made me a little nervous when you have these gigantic buildings and where's the support? That's one of the things. Where's the support? Well, you have all these beams running across. You have beams running several hundred feet across? What are your beams made of, first of all? Maybe they're iron. That the Romans figured this out a few thousand years ago. Arches. Why? Because gravity makes things settle. So if you start with an arch, you've got more stability. That's one of the things, although it would be at a really small level. But the idea being, how do you build a large building and not have it all come crashing down?